Oxidation-reduction reactions are an important class of chemical reactions which are abbreviated redox. Combining two words, oxidation-reduction, to redox reactions. And these types of reactions refer to a transfer of electrons between the reactants, at least a set of two reactants in the chemical reaction. This is an important group of reactions. For instance, the process of photosynthesis, by which plants synthesize carbohydrates from CO2 and water, are essentially a series of complex redox reactions. And batteries, as another example, involve redox reactions. Two examples: sodium and chlorine to form sodium chloride solid, and methane combusting in O2 to form CO2 and water. Okay, so these are examples of redox reactions, and what we're going to learn in this video is how to identify these as redox reactions and then assign to the reactions which species, which reactant is being oxidized and which one is being reduced. First, let's just define a few terms. So we said that a redox reaction refers to a transfer of electrons. In the top reaction, that means that electrons are being transferred between reactants. So specifically in that one, electrons are transferred from sodium to the chlorine gas. In the bottom reaction, electrons are being transferred from methane to the O2. So for a reaction in which a reactant is gaining electrons, we say that that particular reactant is reduced. So chlorine gained electrons and was therefore reduced. In the bottom reaction, since dioxygen is gaining electrons, it is reduced. So reduction refers to a gain in electrons. On the other hand, the other elements in those reactions, the sodium for instance, loses electrons and is called oxidized. In the bottom reaction, the methane, CH4, is giving up electrons to the oxygen, and by losing those electrons, we say that it is oxidized. Okay, so the term that we use more commonly for the reactant that is oxidized, and this is a little bit tricky, but basically the thing that is oxidized is giving away electrons to something else. It is reducing the other reactant. And therefore we call the reactant which is oxidized the reducing agent. On the other hand, the reactant which is being reduced is essentially taking electrons away from the other reactant. It is oxidizing that other reactant, and therefore we call the species which is reduced the oxidizing agent. And so this becomes tricky because we see now that the reactant that is oxidized is called the reducing agent because it ends up giving electrons to something else, and the reactant which is reduced is end up being called the oxidizing agent because it grabs electrons from the other reactant. So in the bottom reaction, the methane which is being oxidized would be called the reducing agent. It reduces the O2. The O2 is taking those electrons from the methane and therefore is the oxidizing agent. So how do we identify these? Okay, there's two easy ways to identify, or fairly easy ways to identify a reaction as a redox reaction. And the first one is used commonly by biologists, and that is we look for a transfer of oxygen or hydrogen, okay, between species in the reaction. And specifically, reduction is characterized by a loss of oxygen around an element or a gain of hydrogen. And oxidation refers to the exact opposite, a gain of oxygen or a loss of hydrogen. And certainly the gain of oxygen part makes sense from the term oxidation, gaining oxygen, oxidation, that seems to go together pretty well. And it turns out that we can identify the combustion of methane as a redox reaction using this sort of simple method. If we look at the carbon in that reaction, it is bonded to 4 hydrogens, and in the product, carbon's bonded to 2 oxygens. Therefore, the carbon in that reaction, right, goes from having 4 hydrogens, it loses hydrogens, to gain 2 oxygens, and therefore is oxidized. Oxygen, on the other hand, ends up getting 2 hydrogens attached to it, so a gain of hydrogen, and therefore the oxygen was reduced. And so you can identify a redox reaction by this method. But of course, not all reactions involve hydrogen and oxygen. For instance, the top reaction between sodium and chlorine. In that case, we're going to use a more formal method, which is to assign oxidation states. So a change in oxidation state can be used to identify a redox reaction, and we're going to go over a list of steps and rules by which we can do that. Simply though, just really quickly, for the top reaction between sodium and chlorine, just to illustrate what I mean by change in oxidation state, if you look at the sodium chloride in the product, right, sodium we know has a +1 charge and chlorine a -1 charge. If we take those to be the oxidation states, sodium is +1 and chlorine -1. In the reactants, though, notice that we have just the elements, sodium and chlorine. Sodium has no charge on it, and therefore its oxidation state we call 0. And chlorine, also being a neutral element, has an oxidation state of 0. Therefore, the sodium goes from an oxidation state of 0 to +1, i.e. it is oxidized, and the chlorine goes from 0 to -1. In other words, it gained electrons and was reduced. And so by assigning those oxidation states and then looking for a change between the reactants and products, we can identify a redox reaction as occurring in that particular chemical reaction, sodium plus chlorine going to sodium chloride. There's a more formal set of rules for doing this, and those rules for assigning oxidation states, and I should note that another term for oxidation states is the oxidation number for an element in a compound or free element. And I just want to also stress that this set of rules that we're going to go over are for bookkeeping only. The oxidation states or oxidation numbers don't necessarily refer to a charge on an element like we have in an ion. So it is an electron bookkeeping method and does not necessarily refer to or correspond to an actual charge. Okay, so the first rule, free elements For instance, nitrogen, oxygen, iron, phosphorus, these have oxidation states of 0. So free elements have oxidation states of 0. And when we do this, we'll write a little 0 above those in the reaction. 2, monoatomic ions, for instance, Na+, calcium 2+, iron 3+, and O2-. These monatomic ions have oxidation states which are equal to their charges. 3, in compounds, and this means, and this is in order of priority, so as you assign oxidation states to elements in compounds, I would go down this list in this order. In compounds, number 3 of the rules, alkali metals are always +1, and alkaline earth metals are always +2. Okay, so if you see a lithium or sodium, potassium in a compound, you always assign its oxidation state +1. And for the alkaline earth metals, such as magnesium or calcium, you assign those metals an oxidation state of +2. Fluorine always has an oxidation state of -1. Next, oxygen usually has an oxidation state of -2. So in most compounds, you'll assign oxygen to be -2, except when it's bound to fluorine. Fluorine has higher priority, so you would assign its oxidation state -1 first, and then look to assigning oxygen's state. 6, hydrogen has an oxidation state usually of +1. The exception is when hydrogen is bound to a metal. In those cases, the metals get priority, and hydrogen is likely to have a different oxidation state. And then finally, for assigning oxidation states of all the other elements in a compound, we use this last rule, which is the sum of the oxidation states of all atoms in a particular species, and this includes neutral and polyatomic ions, neutral compounds and polyatomic ions. The sum of the oxidation states must equal the net charge on the species. So you look to, a compound like CO2, which is a neutral compound. It has a total charge, therefore, of 0. It is neutral, and therefore the oxidation states of the elements in the compound must add up to 0. For a polyatomic ion, for instance, nitrate, which has a -1 charge, the oxidation states of the individual atoms must add up to -1. So let's go over some quick examples. H2O first. So we assign oxygen its oxidation state first. Rule number 5, it has an oxidation state of -2. And therefore hydrogen must have, regardless of whether you go by rule 6 or not, it does end up following rule 6, have an oxidation state of +1. That means with 2 hydrogens, it's +2 total. In OF2, our priority dictates that we assign oxidation state of -1 to fluorine first. There are 2 fluorines in the compound, and therefore the total is -2, and I usually write that in parentheses to distinguish the total from the actual oxidation state on fluorine, which is -1. So each fluorine has an oxidation state of -1. That totals -2, which means that in this case, oxygen has an oxidation state of +2 for the total charge in the compound to be neutral. In sodium chloride, we know that alkali metals are always +1, and therefore chlorine is assigned an oxidation state of -1, so that the total charge on the species is 0. In sodium hydride, sodium again assigned an oxidation state of +1, which means that now hydrogen has to be assigned an oxidation state of -1 for the total charge on the compound to be 0. For perchlorate anion, notice that we have a total charge of -1. Oxygen is assigned an oxidation state of -2. There are 4 of those, so each oxygen with -2 ends up totaling -8. Since the net charge is -1, that means chlorine has to have an oxidation state of +7. Bromine, elemental bromine, from rule number 1, we see free elements have oxidation states of 0, so we'll write a little 0 above that for its 0 oxidation state. But bromine in BRF3, the compound, will not have an oxidation state of 0. What we do is we assign, based on our set of rules, number 4, fluorine has an oxidation state of -1. There are 3 of those, so that totals -3. Therefore, bromine in this compound has an oxidation state of +3. Let's look at how to identify, now using these rules, redox reactions. And we're going to start with a simple transfer of electrons between zinc and copper 2+. So imagine taking some solid zinc and plopping it into a blue solution of copper 2+, and what happens in that is that you start a redox reaction in which copper starts to form a solid, and zinc is converted to aqueous zinc 2+. Now this one is pretty easily identified as a redox reaction. We're going to go through the formal process, though, of assigning the oxidation states to do the identification. Zinc, since it's a pure element, has an oxidation state of 0, but in the product it has an oxidation state equal to the charge of the ion, which is +2. Therefore, zinc is oxidized. It has lost electrons, which is why its charge went up. That also means that zinc is the reducing agent. The zinc solid in the reactant is a reducing agent. It is giving up electrons to something else, and of course that something else is the copper. Copper starts with a 2+ oxidation state as copper ion in solution. But in the product, copper is a free element, has an oxidation state of 0. That means that copper is gaining electrons in order to go from +2 to 0, and copper is reduced. This also means that we call copper 2+ in the reactants the oxidizing agent. Now for simple reactions like this, we can actually split up the reducing half and the oxidizing half of the reaction. If we look at the zinc is being oxidized and copper is being reduced, we can split those apart into what are called half reactions. So for instance, zinc goes from neutral zinc solid to zinc 2+. That means electrons are being removed and would end up as a product. Right? So we write the 2 electrons as if they were a product. Of course, they're never free. They're always directly transferred to another reactant. But here what we've done is written the part of the reaction in which the zinc is oxidized. So this is the oxidizing half reaction. Copper goes from copper 2 plus to copper neutral elemental copper, and that means that it must have gained 2 electrons. Right? It requires, if we add 2 negative charges onto the copper 2 plus, it would become neutral copper. Just as taking away 2 electrons from a zinc would result in the zinc 2 plus. In this case, we have written out the reducing half reaction of copper 2 plus to neutral copper. If we add those 2 reactions, the electrons end up canceling out. We have 2 electrons on the reactant side and 2 on the product side. Those cancel out, and the sum of the half reactions should equal the complete reaction that we have above. Zinc plus copper 2 plus goes to zinc 2 plus and copper. And one more example, we'll look at the combustion of methane. In this case, the methane, and we have already identified this as a redox reaction by our transfer of hydrogen and oxygen previously, but let's do this by assigning oxidation numbers. The carbon above is attached to 4 hydrogens, and hydrogens get priority. They're assigned oxidation state of +1. There are 4, and that totals +4, which means that the carbon in methane has an oxidation state of -4 in order for the total charge to add up to 0. In the product, carbon's attached to 2 oxygens. They are assigned oxidation state of -2. There are 2 of them, and so the total charge is -4. And this means that the carbon in CO2 has an oxidation state of +4. And notice that carbon from the reactant to the product goes from -4 to +4. And therefore carbon is oxidized. Remember that if it goes up in charge, that means it lost electrons and therefore was oxidized. And this also means that methane is the reducing agent. The electrons that are taken from carbon are going to be given to something else. So the methane is essentially giving up electrons, in this case to O2. O2 starts out with a oxidation state of 0 and ends up in H2O. We assign oxygen a -2. Hydrogen is +1 for a total +2 to keep the compound neutral. That means that oxygen went from 0 to a -2 oxidation state, and therefore oxygen gained electrons. It was reduced. And this also means that oxygen, dioxygen in the reactants, is the oxidizing agent. Okay, so that is identifying redox reactions, assigning which species are oxidized and reduced, and labeling the reactants as being either a reducing agent or an oxidizing agent accordingly.